Hi everybody, my name is Sean O'Kane with Chip Estimate TV. We're here at CDNLive 2013. I'm here with Cadence, Samsung, and ARM talking about the 14 nanometer FinFET. Now, collaboration is a very key component to achieving first-time silicon success at advanced technology nodes. So what we're going to do, we're going to take a deeper look into the technical aspects of this exciting new logic process node. So with me today is Allen Lin, Foundry Interface and PDK Manager at Samsung Semiconductor Incorporated. Rahual Deokar, Product Marketing Director at Cadence. And Mr. John Heinlein, Vice President, Marketing with the Physical IP Division at ARM. Thank you, gentlemen, for being with me today.
It's a pleasure.
Right. Allen, why is early collaboration at 14 nanometers so critical to silicon success?
Well, the Foundry, EDA, and the design ecosystem is very important for the design wins and for customer time to market. And this early engagement, collaboration with ARM and the Cadence is really to address the new challenges during the process development stage.
Rahual, could you elaborate a little bit more on Cadence's 14 nanometer FinFET from the custom and digital aspect?
Sure, Sean. So FinFET, I believe, is a paradigm shift for the whole industry. And that's why the entire semiconductor industry is looking at it with great awe and anticipation. One of the reasons is it's got the best electrical characteristics that we have seen in a long time. The leakage current is very low. The threshold voltage is very low. What that offers our end users is a best of both worlds in performance and power.
Excellent. John, this is the first instance of a full Cortex-A7 14 nanometer FinFET process. Now, from an implementation standpoint, can you share more details regarding the significance of the Cortex-A7 test chip?
Sure, and I think it's important to remember that we've been engaging with Samsung and with support from Cadence for a long time on test chips for new process technologies. But if you look back just a few years, we did a 32 nanometer test chip, but that test chip in this early stage of the process development was a Cortex-M0, a much simpler core. What we've done with this test chip and this collaboration is take a much more advanced A-profile core with our Cortex-A7. This is a full Cortex-A profile chip that you can buy in a cell phone today. It has a cache and it has all the capability of an A-profile core, but we put this in a test chip so early, and we think that's going to accelerate and de-risk the customers who are using this kind of process.
Great. Allen, could you just share a little bit more details regarding the improvements on the leakage of dynamic power advantages for the 14 nanometer?
Yeah, sure. The 3D FinFET structure brings a lot of challenges to our process development. However, this 3D FinFET structure brings two very important benefits. The first is the wraparound gate to reduce the leakage, and the second is the fully depleted channel. So with these two benefits, we are able to get the performance gain with a lower VDD. And this lower VDD is really the key to reduce the leakage and the dynamic power.
Fantastic. Rahual, so what do designers need to know about the custom IP and standard cell designs using FinFET?
So FinFET, at least three challenges come to my mind for the full custom and standard cell designs. One is for FinFETs, the industry is using SADP, or self-aligned double patterning, instead of the traditional LE, which is the layout edge kind of configuration. And that is very restrictive in terms of the grid that the fins get localized to. That's something that the standard cell tools and the designers have to get used to. The second is the transistor width itself. In the traditional planar transistors, transistor width could be varied almost arbitrarily. But now you have these discrete fins, and you can go only in discrete digital kind of steps, right? That's something, that's a new challenge. And the third key challenge is the parasitics itself. Now you have these fins which are up in a third dimension, in a z-axis, and that increases the capacitive and resistance effects. That adds to the Miller effects and hence the performance. And that's something that the designers need to kind of model.
Continuing with the collaboration theme, John, we've heard a lot about the need for this collaborative effort. and early optimization at these advanced nodes. Now, what does this mean for from ARM's perspective?
Right. We believe that our design methodology is such that it delivers a very high quality, highly manufacturable result. And so actually we believe we're ahead of the curve on anticipating some of these trends. But when you look at an advanced core like an A7, it really forces you to be sure you're looking at the kinds of structures that you need to achieve a high megahertz, high performance, and yet low power design. So it's bringing together the two needs on the process side of making sure it's highly manufacturable with the specific needs of a particular core that's representative of the kind of high-end applications that we do in these kind of app processors. So this is a perfect chip to explore both of those trade-offs. So our IP, the process technology, and the EDA flow will all be ready at the same time.
Yeah, Allen, how is Samsung able to significantly reduce the 14 nanometer die size compared to any other?
Sure. Samsung 14 LPE FinFET technology uses a smaller contact party pitch, the CPP, and also we have a smaller SRAM, and also we have the FinFET specific optimized standard cell. So these are the three very key design parameters that we can achieve the smaller die size.
So is the FinFET, 14 nanometer FinFET process development, is it on track?
Absolutely. We have the test vehicle started last year, and our MPW, the multi-project wafer, is ready now for the early FinFET adopters like ARM.
Yeah, clearly double patterning is a huge challenge for designers at 14 nanometer, Rahual, and I know Cadence has done a lot of work at the 20 nanometer process. What is Cadence doing to solve this particular issue?
So as John pointed out earlier, right, double patterning has been an issue even at 20 nanometers. So we've had the luxury to start warming up, to start working on these double patterning issues at 20 nanometer itself. And the need for double patterning it extends the flow upstream. So for the first time in a digital flow, for instance, you need to account for double patterning and rules in the placement step, because you have to place the right kind of colored cells next to each other. From there, we have to extend it down to the optimization, to the routing parts of the flow and the sign-off. So we've had the nice pathway along 20 nanometers to address some of these challenges and extend that at 14 nanometers. So we feel fairly comfortable looking at some of the test chips we have done. Particularly the A7 was a big learning experience, and it was a proof in the pudding of the tool side, where they have been able to look at not only the basic process requirements, but also the ability to extract the best PPA, the power, performance, and area, as John pointed out, from these complex chips, from the A7, for instance.
And continuing, Rahual, talk about Cadence's role with taping out the Cortex A7 test chip at Samsung Fab.
There were three key pieces. One is the process itself. To be able to get early visibility and to model some of the process effects early on along with Samsung. The second was to build in the smartness and the intelligence in the tools that Cadence supports, the entire encounter RTL to GDS and even sign-off flow from RTL physical to EDI system to downstream sign-off tools in ETS and physical verifications. They were enhanced. And the final aspect is when you look at a core like an A7, we are looking at the methodology that goes along with it, the scripts that go along with it, so that what you have is an end product that makes adoption for an end customer a lot easier, brings down the barrier of adoption. So I think that's the big gain in this whole exercise.
Allen, from a technology standpoint, how does Samsung view the success of the Cortex A7 test chip tape out?
Oh, huge.
Good.
So this is such an important milestone for Samsung Foundry process development to go through this collaboration and have a very successful tape out for the ARM Cortex A7. And Samsung's 14LP FinFET technology, low power, and also tighter contact party pitch is right on customers' desire.
John, why don't you just bring it all together, summarize it, the technical collaboration between ARM, Cadence, Samsung on the A7 test chip?
Sure, and I think that the last two answers really highlight the two aspects of it. On the one hand, from a risk reduction perspective, one of the key benefits our customers are looking for is us to reduce the risk of them getting their design to market fast. So by having the tool flow, the physical IP, and the optimized physical IP, and the core and the process all linked together, it highly de-risks the work of the customers need to get their design to market. From the process side, by forcing early on in the life cycle of the process a more advanced processor, the process engineers and the foundry gets to see the kinds of issues we're facing and make sure that that's tuned as well.
Perfect. Thank you so much for joining us today. So for John Heinlein from ARM, Rahual Deokar from Cadence, and Allen Lin from Samsung, thank you very much. My name is Sean O'Kane with Chip Estimate TV.